As you said, my name is Greg McNamara. I work in the data solutions practice here with Cardinal. I've been here almost a year. I've been working with data, either database development, SQL development, report development, for about 15 years now. If you are tweeting tonight, make sure you include the hashtag ArenaTechNight. We get some social presence here. I was told I had to start with a joke, and a coworker sent one to me today, so I hope I get this right. Let me double check here. So, sorry. A DBA walks into a NoSQL bar and immediately leaves because he couldn't find a table. So don't blame me. First thing we want to do is kind of with a show of hands, see who's familiar with NoSQL. Does anybody have any idea what NoSQL is? How about using NoSQL? In a production? No? Okay. Just kind of a personal. Good, good. So run through the agenda here. What we're going to do is we're going to talk about NoSQL, what it is, what it isn't. We're going to discuss the different NoSQL database types. We want to compare NoSQL and the RDBMS relational database management systems. We're going to look at a few use cases and then go through a couple demonstrations. So what is NoSQL? NoSQL is just a name given to a group of database technologies to use to solve a set of specific problems. Normally, NoSQL shares a common set of characteristics. The first, there's a kind of a common misnomer that NoSQL stands for not SQL or does not use SQL, when in fact, NoSQL actually stands for not only SQL. It means there's many mechanisms that you use to access the data. One of those could be the SQL language, but not just the SQL language. Most NoSQL databases are going to use Java or another scripting language to access your data. Most importantly, it's still, in fact, a database. It's built for storage of massive amounts of data. There's three main tenets to the NoSQL database: quick write capabilities, quick read capabilities, and storing massive, huge amounts of data. It's important to note, though, that not every NoSQL database does all three of those well. They are geared for different approaches. NoSQL databases tend to scale horizontally, so you scale by adding more machines to your pool of resources as opposed to adding a bigger machine to run. Performance is very big for NoSQL databases. They've been built to quickly access structured or non-structured data in an efficient, very quick manner, much more quickly than traditional RDBMSs. NoSQL databases do tend to be non-relational, not table-based. They don't always use SQL. In fact, they normally don't use SQL to access or manage the data. And finally, NoSQL databases do tend to be open source. So can anyone tell me who that guy is? So, a little history on NoSQL. The term NoSQL was coined in 1998 by this gentleman here. His name is Carlo Strozzi. I think I'm saying that right. He was developing a file-based database that did not expose the SQL interface. Ironically, his database was relational, so his would not be considered a part of the current NoSQL databases that we consider today. The term resurfaced in 2009 when a blogger named Eric Evans was trying to call out a trend in the surge in new non-relational databases, and it seems like the name NoSQL stuck, for better or for worse. Strozzi later suggested that since the current NoSQL movement departed from the relational model altogether, that NoSQL would be more aptly named NoRel. So there are four main types of NoSQL databases. The first is your key value. This is the most simple and the most fast. You just do a simplistic fast lookup. Just stores a key and a value, kind of a hash table. And there's no need for a fixed data model. Second type is the document database. Document databases will handle heterogeneous data very well. They don't require a consistent data structure, and they're very useful when your requirements and your database layout change constantly. And we'll see a little more of that later. Columnar database is the third type, and they provide some row and column structure, but the data is stored in columns instead of rows. And they do not have strict rules of relational databases. And the final database type, and the one that I think is the most interesting, is a graph database type, where the data is represented by relationships. And the relationship is the most important part of a graph database. So we wanted to take a look at where the activity for the current active open source projects is as far as the database type. You can see here the key value store is definitely, it's at 35 if you can't see that. That's definitely the most popular, and that is because of its ease of implementation and its ability to quickly store and retrieve massive amounts of data. Secondly, we wanted to see what interface languages are being used within these projects to access the data. And you see here, as we saw with the key value store being the majority in the projects here, Java is definitely the leader as far as languages go, followed by C++. An interesting thing to note, though, we don't have SQL in this graph, but it is definitely available as an interface language, and it is being used, as you'll see later. So now we want to take a little deeper dive in each of the database types, starting with the key value store. Key value store, as we said, it's just basically a hash table. It stores a unique key and a pointer to data, as you see in this example here. It's very simplistic, very easy to implement, and it's incredibly fast because it's so simple. You can retrieve that data very fast. When you don't really have a need for store procedures, the constraints, the triggers, any of your higher level database functions, a key value store is a very good solution. Potential uses for these would be web applications when you have content caching and logging. And some popular vendors for these would be Voldemort, Dynamo, and Redis. The next database type is the document database. It's very similar to a key value, where a document is basically a collection of key values. The key value combinations rolled up into a document. Documents are semi-structured, very good for inserting, manipulating, and retrieving semi-structured data. And it has a very loose schema. Compared to a rigid RDBMS schema, the document is very loose, where you could have multiple documents that have completely different sets of columns within the same data area. And then the schema is also very flexible. There's no restrictions on the number of fields that can be added into a document there, so you could add as many columns as you like. Potential use for a document database would be they're very good for metadata stores, and the popular vendors being CouchDB, MongoDB, and Lotus Notes. I want to show you a collection here, an example of a collection of the key value combination. So this would represent one document from this front brace to the back. And we see we've just got a collection here, key value store, first name John, last name Smith, ages 25. It's interesting to note in the phone, we actually have nested within our single key value. The phone is the key, and then this is your value. And then inside of that, you have multiple key values combinations inside that as well. The third database type is the columnar database, as the name implies. data is stored in columns as opposed to rows. A key is associated with multiple attributes or columns within a columnar database. This is good because you don't need to access an entire row, but you can only pull the columns that you need. The flexible design of a columnar database allows the ability to add new columns easily in the future without impacting your existing structure. There's two huge benefits to the columnar database. That columnar nature provides these two benefits. First is performing very high performance aggregation, because most of your aggregation, what's the word I'm thinking of? Regardless, your aggregation functions, your min, your max, your sum, your count, is performed very easily due to the columnar nature. And also, your data is easily compressed because the compression algorithms are done at the columnar level. So potential usage of a columnar database, real-time data logging. And some popular vendors here would be Cassandra, HBase, and Riak. And I've got an example document here, or example of a column store. As you see, where a row you're storing across, where in a column store you're just storing down. In the flexible design, you're not storing where you don't have the need for the data. Another example to look at, we wanted to see, because I thought the columnar data was a little trickier because it does look like it's still storing it as a row. I wanted to see some relational data. And what we've got here, we have two tables. The first is car and driver information. We have 3 rows in there with a primary key, and then some service information for your car. And notice that the key here is your link back to the main table. And this is actually a typo. I apologize for that. So imagine there's a 6 there. So these two tables are linked together according to that key. So here we've got this second view shows what that car and driver information would look like in a columnar view. Note again that that key still ties everything together. And still looks like rows, but it is stored as columns with pointers to the data. So for instance, the top row, this has 5 columns. This one only has 4. And we're not storing anything here. So we're not having to allocate space for those as we would in a row-based system. So say we wanted to see the service information for our car. Well, we can't, because you can't do a join in a columnar database. So what we would need to do, we need a new implementation here that shows how we would store that data together. So in this case, we're adding another row. Another column for our service information. Sorry. Since this is a one-to-many, this column stores multiple records in here. So you do have some row-column structure within here, but this is stored as a column. These multiple service information rows are stored as a nested collection of the key values. The final, and as I said, the most interesting, in my opinion, is the graph database. Graph databases use a graph structure, and they use nodes, edges, and properties. A node represents an entity, such as a person, place, or a thing. Think of something that you would create like an ad hoc Facebook page for, a fundraiser, or a running club, or a musical group, or whatnot. Sorry, the properties represent pertinent information that relate to your nodes. So for instance, if Wikipedia was a node, it may have as many properties as you could, but 3 properties. One would be a website, another would be reference material, and another would be just words that start with the letter W. It all depends on what you're trying to do, what data is pertinent to that particular database. And the final and most important, edges. Edges are the relationships or the lines that connect the nodes. So most of the important information from a graphing database is stored in these relationships or these edges, and the meaningful patterns emerge when you analyze the connections between the nodes and the number of hops between the nodes. So every node through its edges knows about its neighbors, and potential uses, like I said, was social networking is a big user of the graph database. Popular vendors here, Neo4j, InfoGrid, and Infinite Graph. So quick example, we have graphs have nodes, and each of these green dots represents a node. These lines represent the edges between the nodes. The nodes have properties. We have Candy's 31, Bob's 41. He's employed at Honda. And we have a 2012 Chevy Volt. And then the edges also have properties as well. We know that Bob lives with Candy. He's married to Candy. Bob owns a Chevy Volt, and Candy drives the Chevy Volt. So next we wanted to take a quick look at just a few of the features for the 4 types of database types we've talked about so far. A few of the more popular features, first being the table-like schema structure. As I mentioned, the document and the key value, they have very almost non-existent schema, where columnar and graph have a lot, not nearly a rigid schema like in a relational database system, but a flexible, looser schema. Aggregating across the rows, columnar and document databases, with the quick aggregation on that columnar data, you get your mins, your max, your sums. That isn't quite so easily with the other types. Querying or filtering on a specific value. Key value makes this very difficult, where columnar, document, and the graph make that pretty simple. Like for instance, if you want to find everybody that drives a 2012 Chevy Volt. Relationships between entities. As I said, the graph database, the relationship is the most important part, more important so than the nodes itself. And then the partial update fetch, the graph database, it's nearly impossible to do that because it essentially does a lock on the system while that update is performing. Now I wanted to do a quick comparison on the NoSQL versus the relational database. So with the relational database system, you're basically using a SQL interface. But as I mentioned with NoSQL, there are mainly, it's a very different interface. There's many different, depending on which vendor, which type of database you're using. NoSQL is base, and RDBMS is ACID, and we'll get into those acronyms in a minute here. NoSQL uses no schema or a very flexible schema, where an RDBMS, as I'm sure most of us know, have a rigid structured schema. NoSQL tends to generally scale horizontally, while the RDBMS is more of a vertical scale. I mentioned relational databases are ACID, and ACID is an acronym standing for atomicity first. All of the work in a transaction completes or none of it completes. And a good way to think of this is a banking transaction. If you're withdrawing money from one account and depositing it in the next, if something happens in the middle there, you want to make sure that that withdrawal gets rolled back if it did not get deposited into your other account. Consistency. Consistency says that a transaction transformed the database from one consistent state to another. So data written to the database must abide by the rules of your database. Isolation. Isolation just says that any type of changes in the database need to be isolated until the transaction completes. So for instance, going back to the banking example, during that withdrawal, if you're hitting the database in other regard, you can't see that withdrawal until that transaction is complete and it commits the withdrawal and the deposit. And finally, durability. So the results of a committed transaction survive any type of failure, and the state will be durable. So basically what that says is once a transaction is committed, it's committed forever and won't uncommit unless you take actions to actually do that through another transaction. Now the opposite of that, NoSQL, is BASE. BASE is an acronym that says basically available. Indicates that the system does guarantee availability in terms of the CAP theorem, and we'll talk about the CAP theorem in a minute. This basically available is talking about the distributed system where you've distributed your database across multiple nodes. So it says that one node can go down and you can still access the rest of the nodes. So your system is still available. You kind of have a service guarantee. Secondly is soft state. Soft state indicates that the state of the system may change over time without input. This is because of the eventual consistency model. These kind of build on each other. So the next is the eventual consistency model. The eventual consistency model indicates that the system will become consistent over time given that the system doesn't receive input during that time. So I'm assuming that you're here because you have some type of background in relational database management, or maybe not. So with that said, does this bother anybody else the way it bothered me? That the first time I read this, I had to back up and read it again, because coming from the reporting and reporting background and the SQL database development background, there's such a focus on consistency and accuracy of your data. And it seems like this is just kind of like, it'll be right sooner or later. It'll be eventually, we guarantee it's eventually going to be right. And it seemed to me that that's the wrong way to do business. But the more I read about this, I saw that the base system, it's compromising consistency in exchange for availability. And so it's just, depending on what type of system you're using. So for instance, the availability advantage tells you that because of the distributed nature, your system can always be on. So for instance, if you're running a web app or another type of a mobile-based business and you can't afford to be down for a single moment, you can be a little more lax with your consistency given that your system is always available. I mentioned the CAP theorem. So the CAP theorem, another acronym, first we have consistency. This means that the data remains consistent after an operation is, after a transaction executes. The A stands for availability. System is always on. Like we mentioned before, you kind of have your service guarantee. It's always going to be basically available. And the P stands for partition tolerance. It means that the system functions even when there is some type of unreliable communication between your servers. Theoretically, it's impossible to fill all three of these at the same time. So the CAP theorem states that you have to pick two of these requirements. There are three different types of combinations of these requirements. And the description of each of these is first starting with the CA. This is your relational database model. And it says that your data is consistent and available. You may have a partition that occurs, and then your system blocks. So you're picking up the C and the A, and you're sacrificing a bit on the P. The next is the CP. And this is MongoDB, HBase, Redis, and Google's Bigtable. This says some of your data may not be accessible, but the rest is consistent and accurate. The third type is AP, and examples of that would be Cassandra, CouchDB, and Voldemort. And this says that your system is available under partitioning, but some of the data may not be accurate. And one quick note, note that these database groupings here are not database type specific, but rather they're an attribute of the specific database because CouchDB and MongoDB are both document types. So it's not an attribute of the document, or I'm sorry, of the database type, but rather the specific database. So we wanted to look at a couple of use cases to help define why people are using NoSQL specifically. First is size. Everything is big. Big data, big number of users, big number of computers. Everything is big. More data, more. Second, we have fast access. This is the second most cited virtue of NoSQL. If you have all this data, I need to be able to access it quickly. Third is write performance. Massive write performance with high volume data. For instance, Facebook needs to store 135 billion messages a month, and Twitter has storing 7 terabytes of data per day. So they need to be able to write that very quickly. We talked a lot about the distributed nature, so there's no single point of failure. And then finally, using the right data model for the right problem. Different data models, different database types are designed, developed to solve different types of problems. Isn't it better to solve a graph database or graph problem in a graph database? Now we want to look at a few more a deeper dive into a few more use cases, and specifically around the graph database. And I mentioned the most important, or the biggest use that we've seen so far for graph databases is a social perspective. Graph databases are very good for storing information about relationships, especially when the relationship is more important than the items that have the actual relationship. Also, graph databases are very good at analyzing how closely things are related, specifically how many steps from one node to the next. So how many of you get emails from LinkedIn suggesting that you connect with some person or you join a group? Those are all based on your current connections. Those are all based on edges and properties. We are all nodes within LinkedIn. Also, we get requests from LinkedIn to complete our profile. They're looking for ways that we can add more edges, add more properties to your node. Second use case we have is the NSA. And I'm sure we've all heard of this analysis of relationships between people, discovering terrorist cells. Surely the NSA is using a graph database here, especially when the number of hops, inferring relationships from your phone records, your social media interactions, and your email correspondence. Sometimes they may have a Twitter handle or a phone number, but the relationships are not known. And they can still use a graph database to infer groups that relationship is part of, or how central an entity is to an existing group that they're aware of. And then just last week, the House Intelligence Committee passed the USA Freedom Act. I don't know if anybody heard about this. It's regarding the phone bulk metadata collection that the government has been doing. And this limited the government from 3 hops to 2. So they're shrinking the government's data collection, which is almost certainly a graphing database. The final graph database use case is dating sites. The dating site AYI uses a 1 billion person social graph to improve the likelihood of finding a match. And what that graph does here, using your connections and your relationships, they recommend matches based on friends of friends and friends of friends of friends, on the likelihood that you're going to go out on a date with someone who knows someone who you know, rather than a complete stranger. In just the last 6 months, more than half a dozen online dating companies around the world have implemented graphing databases. Got a couple document DB use cases here. First is Shutterfly. Does anybody use Shutterfly? I'm sure we've all received a link that wanting to view someone's album. It's an internet-based photo sharing company. Shutterfly uses MongoDB, which is a document database type. They have a persistent share of more than 6 billion images. They use their document database to capture those images. They capture the metadata about the images and the comments or tagging. Anybody tags a photo, they copy all of that into a document, similar to the document example that we looked at earlier with the name and the multiple embedded phone numbers in there. So the tagging and commenting demonstrates the loose, flexible schema of a document database. Finally, we have a blog posting. So a document database is ideal for managing blog postings. Each blog is represented as a collection of post documents. And then as people comment on that blog, those comments go right into that document as additional. All right, now we want to get into some actual code, do a little demonstration of the Mongo database. Bear with me 1 second here. So I've already got the Mongo database process running. So Mongo runs on the command prompt. And I'm just going to run mongo.exe. That will get me started. And you'll see here it's trying to connect to a database called test. And I can pass a pretty simple command called db, and that'll let me know which database I'm currently looking at. And then if I type another command called show dbs, it will show me all of the database I have in my system. All right, so I didn't, bear with me 1 second. I can also do a command called use, which will transfer me, or move me over from one database to the other. So I'm going to move over to MyDB. I'm going to see that I'm actually using MyDB. Then I'm going to run a db command called db.drop_database. And then I dropped MyDB. If I go back and show my databases again, you'll notice that that's gone. I'm going to switch over to use another test. I just want to drop these real quick so we can do some examples. OK, so I want to switch over. Can everybody see that? So I'm going to switch over. I'm pointing to the MyDB database now. And what I want to do is I just want to create a couple of simple sample documents. So here I've created a document. It's called J. It's just a key value pair, name, and the word Mongo. Then I'm going to create another document called K. So all I've done is created two documents. I've not inserted them in a database or anything. So let me do first show DBs, and I want to show you that we're pointing to the database MyDB, but when I do a show DBs, it's not there. And the reason is because a database doesn't get created until you actually insert data into it. So I'm using MyDB database. Within MyDB database, I've created two simple documents, but MyDB database still doesn't actually exist because I haven't inserted that in the database. So what I want to do now, I'm going to go ahead and insert that document J. I'm within my database, I'm creating a collection of documents called test data, which is just an arbitrary name for a collection. And within my current database, the collection is called test data, and I'm inserting that document J. So when I did that, three things happened. Number one, it created the MyDB database. Number two, it created the test data collections. And number three, it inserted that document J into my collection. So now, if I type show DBs, you'll see that MyDB exists. And within my database, we're still in the, we can check that again, we're still in the MyDB database. And I can type show collections. And this will show me all my collections. That system indexes is a system default that happens within every collection. Within every database. But we've got our test data collection inserted there. And within test data, we should have one document called J. So we can pass a simple find command to our test data collection, and it'll return that document J with the item's name and Mongo. So when we created that document J, we also created a document K, which is still sitting out there in virtual space. So we can go back and add that as well. And then if we do the call to find again, we'll notice that both of our documents are now existing. Pretty simple. So now I want to switch over. I want to do a different example. I'm going to use another database now called another test. And see, we're pointing to another test. Let's create a more complex document. And what I want to do is reproduce the document that I used in my example for the document databases. You'll see here, this is where we had our first name, last name, our nested phone information, and the age of 25. So you don't get any type of success signal. They'll let you know if you fail, though. So now we have that document A created, and we need to insert that into our another test collection, and then run a send a find command. And we see our object exists with the first name, last name, the phone information nested inside, and then the age. I want to do another quick example of how we can I want to import a bulk, import a file. I want to import a file into a new database. So I do not have an existing database. And another thing to note, this is an executable. So I had to open a new command prompt. I'm not within the Mongo shell that I was in before. This is in a different command prompt. And from the bin folder, which is like the default install, I'm running this Mongo import exe. I'm passing arguments. The database argument is just called test. I'm creating a collection called zips. And here's the file location for this zips file, which is a JSON file, JavaScript object notation. And you notice we've imported 29,470 rows. So let's look at that sample file. So this is the file that we just imported. And you notice it's just a collection of key values. You've got cities, you've got your longitude and latitude, city population, the state, and then zip code. So what kind of aggregation or querying can we do on that? First, we can do a pretty simple on our DB, zips is our collection, and we're going to do a find. Did I do that? Oh, I'm sorry. Pointing to the wrong database. When we do a find, you see the information that we imported in there. We can type it to iterate through that data. So the first aggregation I want to do, I want to find all the states with a cumulative population of greater than 10 million. So I think it's a pretty straightforward query. We're aggregating, we're grouping, and we're grouping on the state, creating a new column here called total pop. We're summing the population column as it exists in the database now. And then we're using the match to just return where the total population is greater than or equal to 10 million. I can show you. Here would be the equivalent SQL statement. Just doing a simple select, we're grouping, and with a having clause. And you see we get results about what you would expect, the states that you would expect, anything over 10 million.
So does that mean then that new column you created stays documented after you create it, or does it only live for as long as you're doing it?
Yes, yes. That's part of this group here. It basically creates a virtual document. And that only exists as long as the query runs. We can't access that later. Got one more aggregation here. I think is kind of cool. Let's get the average city population by state. We're basically doing the same thing, only we have multiple groupings. We're grouping on the state and the city to get the sum of the population per city. And then we're grouping that on the state to get the average of your city population. So then we see for every state, the average city population for every state. We can iterate through here. And that's really it for Mongo. Real quick, I wanted to take a look at Cassandra. So let me pop this open real quick. It's another command line utility. Sorry. So in Cassandra, you use what they call a key space, which is similar to a schema in SQL Server. And you create a key space here. I'm creating a key space called demo. And we can view that key space by using the describe function. And here you see these three are system key spaces that exist naturally: system, ops center, and system traces. But you see that demo does exist there. So we also need to kind of point our focus here and set this over using the same use command. So we want to point and we want to use demo. You see we're using demo. And the interesting thing and very nice thing I think is about Cassandra is you get to actually use SQL. So we are using the structured query language here. Basically the same syntax. Creating our table here. If we want to see our table, this describes our schema. Now, a whole lot just happened there, but here's the part that we created. Then it adds on the fluff that the database naturally creates, but it also has these other tables that it creates as part of its process, its logging and whatnot in there as well. So if you have familiarity with the SQL SQL language, you can see we can run some pretty simple inserts here. And then we're just querying. do a quick update here. I'm going to take Jane Doe, who currently lives in Beverly Hills, and we're going to move her to San Jose. You see that the data is updated. With a lot of NoSQL databases, you have a lack of a good, nice-looking interface. You're usually on this command prompt here. I think there's a movement now to increase adoption, and they're trying to get people to move over into the NoSQL world. So they're trying to give you, make it a little easier on the developers. And DataStax is somehow affiliated with Cassandra, and they've created this pretty nice little dashboard here. You see they've got storage capacity, cluster reads and writes, your disk I/O. They have performance information. Shows you your write request, your latency, disk utilization, and also your schema. You can actually add schemas. You can add, create tables within this interface here. This is the one that we just created here. Oops. Sorry. And it shows you the insert the create statement that we used for that. With that, I think that is about it. Do we have any questions? Cassandra? That was a, you asked me too quick. I know you know the answer. I had that in my notes, I'm sorry. What's that? Oh, yeah. Commoner database, right.
Was that DataStax come installed? Or was that an extra tool?
It was. It's just a URL. Yeah. All right. If there's nothing else, we've got more refreshments. I don't know what time the pizza is coming, or. Okay, 7, so we've got about 5 minutes to go have another drink, and then what time is 7:30 is the... So we're all done.